Hi, and welcome to another video in the series about probability theory, the logic of science by Jaynes. This video is going to be about the material from chapter 2 of the book called Quantitative Rules. In the last couple of videos, we've talked about how Jaynes's program of the book is to describe probability theory in the way that we understand it mathematically as a consequence of some more fundamental criteria for consistent logical reasoning in the presence of incomplete information, so what he calls plausible reasoning. In the last chapter, we talked about what that means conceptually, and we gave some kind of qualitative conditions that we expected to be subject to, but in this chapter, we actually really put that into practice and look at the quantitative consequences of those assumptions. And what we're going to actually get to by the end of the chapter is the mathematical rules of probability that you may have seen and that we're kind of familiar with theoretically. So last time we talked about these three kind of desiderata, what Jaynes calls desiderata, conditions for plausible reasoning that we kind of agree upon as being generally right. The first one was that plausibility is going to be represented by a real number. And we talked about kind of what that means. The second one is that it has some qualitative agreement with common sense in one or two particular examples. And the third condition is that it is consistent in the sense of structural consistency, meaning if you can calculate a number in more than one way, you should always get to the same answer. And again, the framework that Jaynes lays out is that we're kind of programming these rules into a robot or a computer, and the goal is to be able to give it a statement, a logical statement, and have it give back this plausibility number, and that system should be subject to these rules. I think at this point it would be a pretty fair criticism to say these desiderata don't have a whole lot of content, right? So we said, okay, our program in the book is we want to program a robot to reason consistently about plausibilities and to represent those things as real numbers. So what conditions should that satisfy? Okay, number one, they should be real numbers. Number two, they should agree with common sense. And number three, they should be consistent. It's, congratulations. That's just restating kind of the problem. But really, I think where we get to in this chapter, hopefully you'll see, is that is where these conditions kind of like the rubber meets the road. We actually get some real consequences, and we put into very clear mathematical language what we mean by asserting these kinds of things like agreement with common sense or structural consistency. Okay, so that's really kind of the important content of this chapter. So let's just start with the first kind of big problem that we want to attack is the problem of combining statements together and reasoning about the plausibility of a joint statement. Okay, so what that's going to look like will be expressed in terms of what's called the product rule. Okay, so that's what we're trying to get to. Okay, so the basic setup here is that we have some joint statement involving two propositions, and we want to understand the plausibility of both of them at the same time. Okay, so the question is sort of how plausible is A and B in the notation that we laid out last time, sort of Boolean algebra notation. And always we're going to write conditional on background information C. So actually this symbol means the plausibility of A and B given C. So I guess I could just say, instead of how plausible is it, I could say, what is this number? Okay. And in particular, what is this number in terms of other possible numbers that we might be able to reason about? So plausibility of A, plausibility of B, etc. Okay, so if we think about maybe more the deductive point of view, so if we were just trying to reason about whether these things are true, we could imagine going about that in a couple of different ways. And one way we could attack it is to say, well, okay, we're trying to reason about this joint statement A and B. So the first thing we could reason about is, well, is B true? Is B a true statement? Sorry, true. And then maybe as step 2, maybe once we agree on how true B is, or whether B is true, we could ask, is A true? Okay, so that would be kind of a natural way to break down this combination of statements if we were reasoning about their actual truth. And essentially what we kind of imagine is that reasoning process should carry over to reasoning about their plausibilities as well. So in the situation where we're just interested in how plausible it is, it's natural to kind of expect that the first thing we might attack is how plausible is B, so reason kind of about B, and that would involve the number plausibility of B given C. And then maybe once we agree on how true B is or how plausible it is, attack the question of, all right, now how plausible is A, given that kind of background assumption. So we might invoke at some point here plausibility of A conditional on the assumption that B and C are true. Okay, so that's a rough kind of description, but what we're basically gonna imagine is that we can put that into a functional relationship. Okay, so our guess, or you could call this our maybe kind of broad assertion, is that actually that's all we need to reason about the plausibility of A and B, and there's going to be some functional relationship that puts this number in terms of these two numbers. Okay, so there's going to be some function, call it f, that we can write A and B, plausibility of that, as a function of first B and then A, assuming B. Okay, so at this point in the book, Jaynes does a little bit of a digression and talks about, why is it natural to kind of think that is a reasonable functional relationship. For example, we could ask the question, why not something like just some other function of plausibility of A and plausibility of B independently? Why can't we write the function that way? Which is a reasonable thing to ask. What he essentially argues is that you can work your way through a number of common sense examples and see where this kind of plausibility reasoning would break down. Okay, so first of all, let's say this was our guess as to the functional form. Imagine that A was a statement like, the next person you meet will have black hair, and B is the statement, the next person has blue eyes. Well, it's reasonable that we might expect we can reason about kind of plausibility of the next person having black hair, and we can reason about the plausibility of them having blue eyes, and then we could reason about, or what's the plausibility that the next person you meet will have black hair and blue eyes, so that would be the compound statement. But in reasoning about that compound statement, we probably need some understanding of the interaction between these two characteristics. So in contrast to this, let's say that you had statement A was the next person you meet will have a blue right eye, and the statement B is the next person you meet will have a brown left eye. Right? So again, we can reason about plausibilities of those statements independently of each other. But then if we want to ask the question, how likely is it that the next person you meet will have a blue right eye and a brown left eye, we would imagine that's very unlikely, basically almost impossible. And the reason for that is that there's an interaction between these two statements that isn't captured by either one of the plausibilities in isolation. Okay, so this is kind of the basic common sense argument for why we need terms like this one, A conditional on B and C, to enter into the function somewhere. And Jaynes basically says you can go through all of the other possible functional relationships that you could imagine writing down, and you can eliminate all of them using these kind of common sense examples. The only other one that you can't eliminate, that we maybe just write down here, is that it could be the case that it's a function of the propositions just written in the other order. Okay, so instead of taking B first and then asking about A, we could write A first and then asking about B conditional on A and C. And that, again, would give us some common sense functional relationship that at least isn't ruled out by these kinds of examples. This is going to be our basic functional relationship that we assert that plausibilities are going to obey. And really the kind of move of this chapter in the book is going to be to take these functional relationships and derive some mathematical consequences just using kind of math theory. So this is going to be true for both the product rule and the sum rule that we're going to talk about later. Just make some room. Okay. So where we get to, erase this too, is if we call this, say, variable here, let's just denote that by a little x, and this one let's call y, and this one we'll call actually little u, then the claim is that for any triplet of statements, A, B, and C, we can always express this plausibility of the joint statement u as this function of x and y, where x is plausibility of the second one, and y is the conditional plausibility of the first one. Or we have another functional relationships with it that we just erased, but this is the one we're going to stick with for now. So then the next kind of question is, what do we know about this function, right? So we talked about last time one of the consequences of this common sense desideratum, the second condition, being some directional agreement between this joint plausibility and plausibilities of each of these variables. Okay, so in particular, if we imagine instead of x, we have maybe some x prime, right, where x prime is bigger than x. Okay, so we've updated our conditions so that conditional on background information, this statement B is made a little bit more plausible in such a way that we haven't changed the conditional plausibility of A given that background information. The question is, in which direction does the function move? And what we said last time is that it has to go up. Okay, so we get u prime, which is a function of those things, and it must be the case that u prime is at least a little bit big, little higher, or at least is not lower, I should say. And again, to kind of think through that in terms of an example, you could say, okay, let's say we're reasoning about the joint proposition, it's going to rain tomorrow, and there was once life on Mars. Okay, so B is the statement, it's going to rain tomorrow. A is the statement, there was once life on Mars, and A and B is their joint statement together. If we have kind of plausibilities for those two things in mind, and then we get, let's say, some weather forecast information, so we get some update about the likelihood of rain that makes it more likely that it's going to rain in our estimation, but that doesn't affect our understanding of, given that it's going to rain tomorrow, how likely is it that there was once life on Mars? It doesn't really matter. Then our joint proposition, the plausibility can only go up. Maybe it's the same, but probably it's going to go up. All right, so that's just, again, our kind of common sense directional agreement of these plausibility functions. But what that means mathematically, if you kind of think about it and write these things out, is that the derivatives of this function in each one of the two variables, okay, to put this in sort of calculus language, the partial derivatives are going to be positive for each variable, and actually the function's positive, and probably what comes comes before that is even thinking about that the function is continuous. Okay, so again, this is some commonsensical kind of thing, but you can imagine that if our plausibility gets updated by a very infinitesimally small amount, we don't want it to be the case that now our joint plausibility assignment jumps from 20% to 80%, right? So there's some kind of stability in these plausibility functions, which is expressed in the continuity of this f, and there's a directional agreement, which is that it's sort of monotonically increasing in each variable. Okay. That's probably as far as we're going to go, and we could say more about the function. The next thing to consider is, okay, what happens if we apply this to more than two propositions at once? Okay, so let's say that we have a situation like this, where we have actually three propositions conditional on some fourth background information, and we want to attack the joint plausibility of all three. Well, we know that we can write this in a couple of different ways. So first of all, we can write ABC as A and B and C, right? Or we can write it as A and B and C. And so basic kind of property of the logical arithmetic that we described last time is that the AND operation is associative in this way. So we can say, all right, A and B together and C is the same as A and the joint proposition B and C. And then if we put that into our plausibility calculator, what we'll get out of this is that A, B, C given D, this plausibility that we're after, we can write as the function of the second proposition, C given D, together with the first proposition, AB conditional on CD, okay, which now we have a way of breaking down even further, again according to the rules, so we can write that as plausibility of C given D, and then the second term here is the function applied to B given C and D, comma, A given B, C, and D, close bracket, close bracket. So that's just taking this description of the joint triple proposition and writing it out. But we can also do it the other way because we know that the two are logically equivalent to each other, so we can get to basically the same place. Let me just write it quickly as f of C, conditional on D, B given C and D, that thing together with A conditional on B, C, and D. So we basically just chase through the same derivation but applied to the different to the second formulation of it. And if we write this in terms of these variables and we just kind of give a shorthand, what we'll see is that this function has to obey the following relationship, which is that f of x and y and z has to equal f of x, comma, f of y and z. Now really, in principle, we've only expressed that for one possible triple of propositions, but the assertion is that if this is some general framework that applies to any propositions, no matter how plausible they are, this functional relationship has to hold for any numbers x, y, and z. Okay, at least any numbers in the range of plausibilities that we expect to get back from the robot. Okay, so this is what Jaynes calls the associativity equation. Associativity equation. For pretty obvious reasons, right? It just basically says that this operation of combining two plausibilities together is an associative one, and you can do it in either order. Okay. So then what Jaynes does is to derive a kind of general class of solutions of this problem. And actually, I think that if you're interested in that derivation, the Jaynes book is probably not the best reference for this, because I think The way he describes some things, he skips over some of the steps, and it's not that mathematically rigorous. Basically, it amounts to it's kind of taking derivatives of both sides of this equation and then sort of writing out the consequences of it and integrating things up. The point is actually that this is not anything to do with probability. This is just a general kind of functional relationship that comes up all the time in math. And there is a well-understood theory about what kinds of functions, especially these well-behaved, continuous differentiable functions in two variables, what kinds of functions you can get that satisfy this equation. So I would recommend, maybe finding a different reference if you want to go through the full derivation of the general solution to this problem. It turns out that the general solution to this associativity equation actually you can write it down in a very kind of simple form, which is to say that f of x and y will have to be expressible in some way as w inverse of the product of w of x and w of y, okay, for some other function w that is continuous and monotonic, either increasing or decreasing. Okay, so again, this is a general kind of picture, and w at this point is just some other function we don't know much about, but the point is that any such f that satisfies this associativity equation has to be able to be written in this form. So without going through the details of that argument, maybe it's just enough to see that if we had such a function, it would satisfy this equation. So if we imagine, we were given some w and we wrote f in these terms, so it's the inverse function applied to the product of w of x and w of y, what happens if we just check the two sides of this equation? So on the left-hand side, we have f of x and y comma z, so let's write that as w inverse, okay, of the first argument is f of x and y, so we put that in for x, so we have w of f of x and y. And then the second argument is z, so we have w of z. Okay, so far so good. Now f of x and y we can further write out in terms of w, so we have w inverse of w of f of x and y is w inverse of w of x, w of y, close parentheses, w of z multiplied. Okay, I hope I got all those parentheses in there. Now we have w of w inverse, or the function of its inverse, so we can cancel those two. So we're going to have w inverse of just what's in here, w of x, w of y, times w of z. Now close parentheses, that's as far as we get. And if you apply the same kind of sequence of operations on the right-hand side, I think you probably believe that you get to the same point. Okay, so f of y and z is going to involve w inverse of w of y, w of z. Then when you take f of it, you're going to have w inverse of sort of w of that. And so the w and the w inverse are going to cancel, and we end up with just exactly the same expression. Okay, so it satisfies the associativity condition regardless of what really this function w is. One interesting thing, actually, if you're kind of looking at associativity and you're thinking about what things you know are associative, you might be confused to see this form if you think about the operation which is just the sum, right? So we know that addition is associative, and it's not immediately clear that if f were, say, x plus y, that it'd be easy to write it in this kind of weird form over here. But actually, if you consider the function which is just e to the x, okay, so w of x is e to the x, then what does this f thing come out to be? Well, the inverse function of the exponential is the log, natural log. Okay, so if we write out what is f of x and y, it's the inverse function, so that's log of the product of w applied to x and y. All right. So e to the x times e to the y. Okay, well, e to the x times e to the y, we know what that is. It's e to the x plus y. And now we have log of the exponential, so that just undoes the exponential, and we end up with x plus y. Okay, so it is actually the case that even very familiar functions like just the sum are expressible in this kind of twisted way of inverse function of the product of two functions. The reason why we care about writing the expression in this form and why this is actually going to be good for us will actually be more apparent if we take w applied to both sides. Okay, so one equivalent way to write this is to say w of f of x and y is just what we have inside the parentheses on the right-hand side. Okay, and now if you remember that these x, y, and f are supposed to be plausibilities that we're talking about, basically what we're going to be saying is that w of this joint plausibility is the product of w of this plausibility times w of this plausibility. Okay, and that, if you are thinking about and familiar with probability in your mind, it should start to kind of seem like we're inching up on some probability rules that you may be familiar with. And so that's kind of where we're going. In actual fact, let's just say like one or two more things. So if we consider going about this plausibility question two different ways. So we started with a, b given c, and we said we can write that now as f of x and y, which is going to be w inverse of w of b given c, w of a given b and c. Okay, that's our guess. If we reverse these two, right, we know that the proposition a and b is the same as b and a. So whatever plausibility we get, it's got to be the same no matter which way we write it. And so this is going to also have to be the same as what we get when we interchange a and b here. So it's going to be w of a, w of b given ac. So in other words, if we apply probability, the function w to both sides, we'll have w of a, b given c is just what I written over there, w of b given c, w of a given b and c, but also equal to the second formulation, w of a given c, w of b given a and c. Okay, so this is actually what Jaynes calls the product rule in its first form. Okay. So again, why do we care about this w, and what is this weird function w actually doing for us? Another way to think about it, if you like, is, remember, we're starting from the assumption that we have this plausibility robot, that we give it a logical statement, and it gives us back the plausibility of that statement. And we've assumed, or we've asserted that, in agreement with common sense, it's got to have some functional relationship between joint plausibilities and these individual plausibilities like b given c and a given b and c. We don't necessarily know what that functional relationship is. So maybe we could ask it for these plausibilities for lots of different combinations of statements. So we could say, okay, what's the plausibility of this? What's the plausibility of this other thing given that? What's the plausibility of the two of them together, etc.? And maybe over time we could sort of map that out. But the point is actually that we want to give those plausibility answers a kind of natural scale, right? And we want the scale that we measure it on to be convenient in terms of the relationships that it maintains. So it's kind of like saying, let's say we were asking the robot for the temperature, and we said, okay, what temperature is it? And the robot just said, it's 7. Okay, that's not very helpful unless we know what scale we're on. So maybe to make sense of that and to put that in context, we would say, okay, robot, what temperature does water freeze at? And if the robot says 0, and then we say, okay, well, great, what temperature does water boil at? And it says 100, and we say, okay, great, if if temperature increases by this amount, what does it do to, let's say, energy or some other physical property? And the robot gives us back some equation that we recognize. Then we could translate that and say, okay, you're talking about degrees Celsius or whatever it is, and we could put that maybe in a more convenient scale that's easier for us to work with. So maybe instead of Celsius, we want to work in Kelvin. So this W, I like to think of this as the kind of weight of the plausibility. And it's really just a translation into another convenient system of units that helps us work with the numbers a little bit better. And in fact, one of the kind of particular consequences of this is that if some function W, let's say, works in the associativity equation sense, so it properly expresses the functional relationships of the plausibilities that we're getting back, then so will W to any power, okay, for any p, including negative power. So we can always basically stretch this scale or indeed reverse it, which we'll see is very handy in just a second. Okay, so we have this idea of basically translating the scale of the plausibilities that we're getting back from the robot, and our basic associativity condition implies that there is some scale that we can measure plausibilities on that satisfies this product rule relationship. Now, what is probably helpful then to think about, and what will help nail down some of these plausibilities as actual numbers, is what do we get for some particular boundary cases or extreme cases. All right, so we'll just think about two of those right now. Okay, so one case to consider is the case of certainty. So let's just say, let's assume that A is certain, again, conditional on background information C. So what does certainty actually mean? Well, first of all, it means that if we're reasoning about the joint proposition of A and B, the A isn't really doing anything in that calculus, right? So if we say, all right, what's the joint plausibility that it's going to rain tomorrow and that 2 plus 2 equals 4, well, the 2 plus 2 equals 4 isn't adding anything to the joint plausibility estimation, so we know kind of from first principles that this should be the same as just B given C, whatever the second proposition is. And the second thing we know is that if we throw in some additional information into our background set, it doesn't make A any less certain than it was already. Okay, so again, it's like saying, is 2 plus 2 equal 4 conditional on the assumption that it's going to rain tomorrow? Well, it was already certain to begin with from just our background axioms, so it's no less certain now than it was. So we'll say that this is actually the same as it was before. And if you just kind of write that out in terms of this product rule, write these two conditions out in terms of what the product rule means, one thing you'll see is that, okay, W of A, B given C is going to be equal to W of B given C. All right, that's just applying the W function to both sides of this equation. And so that, according to the product rule, has to be W of B given C times W of A given BC. All right, so we can cancel this W of B given C, the weight of its plausibility from both sides, and we're going to get that this certain condition, W of A given BC, is going to be equal to 1, which is also equal to the weight of just A given C. All right, that's what I was trying to go to. So the point is that certain conditions have plausibilities that get mapped to a weight of 1 by this W function. What about impossible conditions? Okay, so let me just write this down here. if A is impossible, okay, what do we know about impossible conditions? Well, first of all, AB is now just as impossible, right? So it's like saying, what's the plausibility that it's going to rain tomorrow? And 2 plus 2 equals 5, right? Well, that's, no more possible than just A. So whatever we represent by impossibility, we're going to have the same thing. And conditioning on background information, additional background information, doesn't make it any more possible. Right? So whatever it is, it's still impossible, even if we throw more background assumptions into the mix. Okay, so then if we write that in terms of the product rule, what we'll get is that the weight of A given C is weight of B given C times weight of A given C. Right, that's just plugging those two things back into this product rule equation. And now this has to be true for any proposition B. So the only way that can happen is if actually impossibility is represented by either the number 0 or one other possibility that Jaynes mentions, which is that it's positive infinity. Okay, so we don't need to belabor the point too much, but this equation would be okay if you're multiplying infinite numbers on both sides, if you kind of believe that you can do that. The reason we don't have to care about it too much is that actually we've already said here that we can change scales according to any power we want. So in particular, if let's say impossibility was a number like plus infinity, so basically these numbers are going to be coming down from infinity to 1, representing certainty, we can just take their reciprocals and flip the whole scale over and make 0 our impossible weight and 1 being the weight of certainty. Okay, so if let's say W ranges from 1 to infinity, we're going to take a change of variables and we're going to reverse that. Okay, so it's like saying, again, you're working with this robot and you're trying to understand what is the functional relationship between the plausibilities that it's giving back to you for all these different statements, and you're trying to find some W function that makes this equation satisfied. So you're trying to change the scales of these plausibilities to put it in this nice functional form, and you map that out and you do all that, and you get a relationship that works. You sort of find this mapping W function. Then the next question is, okay, so now ask the robot the plausibility of something impossible, right? And if it gives you back the number infinity after you apply your weight change of scale, then that's fine. What we're going to do is just say, okay, now take one over that function, reverse the scale so that it's ranging between 0 and 1, just as a convention. All right, so that's, again, it's just I think like in thermodynamics, sometimes you might work with inverse temperature or regular temperature, and in this case, we're just going to work with the regular one that goes between 0 and 1. Okay, so that's the product rule. So the next thing then to consider that gets a little bit weirder is, what do we say about joint propositions of the form A or B? Okay. So we've kind of got a handle on A and B, at least we think we do. So now the question is A or B. This is going to be understood by the sum rule. So yeah, the basic idea of the sum rule is going to be to first start with consideration of proposition and its inverse. Okay, the proposition A bar or not A that we talked about last time, and again, kind of reasoning from common sense as we did before. What we're going to imagine is that there's some functional relationship that allows us to write the weight of these plausibilities in terms of each other somehow. Okay, so basically what we're going to assert is that if we care about the plausibility of, let's say, not A, given our background information C, it's going to be some function of the weight of the plausibility of A given C. All right, so you see we're already sort of using our assumed W function that changes the scales of the plausibilities to satisfy the product rule. But that's fine. So this is just some functional relationship S. One thing that we can see right away that S has to obey is that if we think about the weight of the proposition or the plausibility of the proposition A bar bar, okay, so we take the bar twice, that's got to be the same as the weight of A. Right? So that's just logical relationship that the not a statement is the same as the statement. So what this then means in terms of the function is that sort of S of any number x has got to give you back the original number x. Okay, so again, this is just assuming that we can kind of realize all possible numbers by these weights. If we apply the function twice, we've got to get back to where we started. It's this sort of symmetric relationship. And in fact, we can even say more about it. So this is going to get a little bit abstract and weird for a minute, but just bear with me. So, okay, well first actually, so let's just think about these extreme examples. So again, by common sort of sensical arguments, you can imagine that, all right, if A is certain, then A bar has got to be impossible. So A is certain, we know that means it has a weight of 1. So and impossible means it has a weight of 0 by our convention. So S of 0, this S function's got to map 0 to 1, and vice versa. It's got to take impossible, certain statements and give us back the number 0. But if we think about the product rule now in terms of what it says about A and A bar, we can write some very kind of interesting relationships. So we'll start with our ordinary product rule. Okay, A of C, B of A and C. And then we'll do the same thing for this kind of joint proposition, but with the proposition B bar in there. Okay, so again, this is all kind of in Jaynes, but it's a little bit confusing where this is coming from. Okay, and so the next thing to do is basically then consider what this S function tells us about these functional relationships if we write out the implications of it. Okay, so let's just do that and see where it takes us. Let's move over here. Okay, so starting from this formulation, right? Weight of A and C, weight of B and given A and C, what we can actually do is switch this to a B bar using this definition of S. So I like to think again of W as kind of the weight of the plausibility. S is a switch function that takes you from plausibilities related to a statement to plausibilities related to its inverse or its complementary statement. So if we just kind of take that and apply it, what we'll get is, okay, first term we're not going to change. The second term we can write as the switch applied to the weight of the plausibility of not B, okay, conditional on background information A and C, which if we look closely enough, we'll see, okay, we have this term in this second equation, right? So we already saw that in the product rule, so we can sort of solve for that and substitute it in here. Okay, so we're going to have weight of A and C, switch function applied to, what is it? It's this term on the left divided by the first term here, so it's weight of A and B bar given C divided by weight of A and C, weight of A given C, excuse me, over here. All right, and similarly, we know just as we did before, that this relationship's got to be commutative, right? So if we start with A and B, right, that's what got us here, that's the same as B and A. Right, so if we just carry through this same sequence of arguments, but with A and B reversed, we know that we've got to get equal to the thing where we replace A and B. So we'll have B given C, switch function of the weight of let's write it this way. B A bar given C divided by weight of B given C. Okay, so I've just replaced A with B everywhere in the equation. And now, again, there's basically some sleight of hand, which is that if this holds for every possible combination of statements A and B, we can apply it to a particular one that we choose. So what we're going to say is, let's let the statement B be written as, this is going to be weird, but just trust me on this, the not of the combination of A and D for some other statement D. Okay, so D is going to kind of be arbitrary. Why is that good? Now, I know that seems like a weird thing to just imagine doing, but it turns out that statements of this form have a kind of nice functional relationship, which you can work out, which is that if we have things like this A and B bar, okay, that's going to be the same as B bar, just on its own. And similarly, B and A bar is the same as A bar. Okay, so I won't write all that out, but maybe just as an exercise, you can convince yourself that that's true. The first one I think is probably the easiest one. So if we say, all right, B is not combination of A and D, so A and not that is A and D, right? A and not A and D, so it's A and D. Well, A and A is just A, there's no extra information there, so this basically on the left-hand side is just A and D, which is the same as B bar, right? Okay, so that, I think, it carries through pretty easily. The other one you have to think about, not A and D, you can write it in terms of not A or not D, and then, or you can build up the truth table and just convince yourself that it's true. I'll leave that for you. And the point of this is that if we then make these substitutions in here, right, so these are true as logical propositions, but then they also have to have the same plausibility. What we'll get if we let, let's call X the weight of this plausibility, A given C, and Y we'll write as the weight of the plausibility of B given C. Right? If you write out these consequences in terms of X and Y, what you'll get is the functional relationship X times S of Y divided by X equals Y times S of X divided by Y. Okay, so I may have to just kind of trust you that you'll work that through, but you can see a little bit of it. So B and A bar, that's what's here, that's the same as A bar. A bar, the way to get its plausibility is to take the switch of A, so that's switch of X, so you can kind of see S of X, weight of B and A bar, so on and so forth. Okay, now this is for this kind of situation of dealing with propositions and their inverses, the same kind of functional relationship that we had for the product rule, meaning that it's a very general kind of relationship that now has nothing to do with probability. And assuming that S is a reasonably well-behaved function, there's actually a nice theory of what are all the possible functions that could just satisfy this sort of relationship for all X and Y in a suitable range, okay? So again, there's maybe some sleight of hand here that we're imagining that by letting D vary, over all possible statements, we can get basically all possible x's and y values. And then if we plug those in here, we get this functional relationship being satisfied on some domain in, say, two-dimensional space. And then it has to then satisfy a certain relationship, or basically the function can be described in a certain way. And that way is actually very nice. So again, Jaynes, for some reason, does the whole derivation. You don't need to read Jaynes to get the derivation of it. But the general class of solutions can be written this way. Page. So it turns out that the general solution to this problem is that S has to be 1 minus x to the m to the 1 over m power, okay, for some constant m. All right, just take my word for it. Maybe a couple of particular examples that might be useful to think about. Well, first of all, if we take m equals 1, which is really kind of the example that we want, in the end, what this is going to say is that S of x is just 1 minus x, right? So probability of the opposite statement of not A is 1 minus the probability of A. That's something that it seems pretty suggestive. Another maybe nice choice could be m equals 2, in which case, if we think about this kind of on a graph, the equation 1 minus x squared square root should be a little bit familiar to you and remind you of the circle. Okay, so if we take m equals 2, what we're basically saying is that the functional relationship between x and s is that they are on the boundary of the circle with radius 1. Okay, no real kind of magic to any particular choice. The important thing is that what this means in terms of x and s is that actually, let's just go back to write these in plausibilities. Remember, x was our stand-in for this variable. So this thing to the mth power plus the weight of the plausibility of a bar to the nth power has to equal 1. Okay, so that's this is just what's on the left over here. We take the nth power both sides, we add this term to the left hand of the equation, and we get this. And this really should start to ring some bells for you and maybe be suggestive of a nice probability rule that we're going to get to. So remember, we have the product rule already, which said that the product of these weights has to satisfy this some functional relationship, A given B and C. We said that actually any power of that weight function is going to also satisfy that equation. And actually, we can just say, all right, let's take the nth power of both sides of the equation. So whatever, if it was true before, this is still true. And all we're going to do now is basically change scales again. So we're going to say, all right, let's just let P, once and for all, be the symbol for this weight function, whatever it was that we chose, to the nth power. All right, and it'll then satisfy the equation P of A bar given C is 1 minus P of A given C, and P of AB given C is the product the normal way. Okay, so basically what we're going to then do is, once we've worked out these functional relationships and we've changed scales to P, we're going to go ahead and just define that as the probability. Okay, so the probability, finally, at long last, probability of proposition A given proposition C is this number P, which we get by changing the scale of the weights of the plausibilities in such a way that these functional relationships have a convenient form. Okay, so the way, again, to think about this is we started from some conditions on logical reasoning and reasoning about plausibilities. We assumed that we have maybe some robot that we're interacting with, or we give it logical statements, it gives us back probabilities, or let's say plausibility numbers. We don't necessarily know what scale those are on, but we can, based on some kind of common sense, we can work out some functional relationships that they have to obey. We then apply some mathematical theory, and we can say what the whole general class of solutions to those functional relationships is. And then we can basically do a little change of scale. So say, okay, it has to be the case that there's some weight function and some switch function that would make these things work. So we'll just change scale once we've figured those functions out, so that we're actually talking about the numbers p, which are the weight function to this nth power, that make our probability equations look very nice and simple. Okay, so it's just basically changing scale or changing variables to a nice convenient form. But it's interesting to note that these are basically the rules of probability that you're probably familiar with, or that you may have seen before. Okay, and these are the forms that in the mathematical theory we would usually take as axioms or as properties of the definition of probability, but really in this case it's just a consequence. Okay, the second one in particular, again, maybe is less familiar to you. This is going to be the whole basis for everything that comes later in the book. So essentially this is what we think of as Bayes' rule, or what you may know as Bayes' rule, and this is going to be the basis for all of our methods of statistical inference in a way that we'll see in great detail later on. But before we get into that, though, I think it's maybe fun to go back and think about the examples that we had last time. We were talking about deductive reasoning and the strong and weak syllogism, and just see how they play out in terms of these probabilities. Okay, so let's do that now. Okay, so let's say we were interested in talking about the kinds of strong and weak syllogisms that we had last time. So you might remember we had, for example, the Aristotelian strong syllogism. So we say P implies Q, and P therefore Q. P therefore Q. That we understand as kind of the strong principle of deductive logic. But let's just see how that plays out. So let's say that our background information C, right? Let's let statement C represent the major premise of that statement, which is that A, let's say statement A implies statement B. Okay, so this is part of our background information. What does that mean in terms of the logic? Well, first of all, the combination now of A and B, given C, has got to equal plausibility of A, given C. Okay, and the reason for that is that conditional on background information C, these two statements are the same, right? Once we have A, we have A and B, right? So writing out sort of the truth table of A and B, and A, under the assumption that C is true, we're going to get that these are the same statements, right? So that means that they have the same probabilities. Okay, A and B conditional on C is the same as A given C. So now if we put that into our product rule, right, what does it tell us? Well, on the left-hand side, we have probability of A and B given C. So we're going to have probability of just A and A given C. And on the right-hand side, we have, let's write it as probability of A given C times probability of B given AC. Okay, so I didn't say that, but you should be aware that every time you do a product rule decomposition like this, right, you can always equally well go the other way, right? So we can just as well say, instead of first thinking about B given C and then A given BC, we can think about A given C and then think about B given A and C, right? And in fact, the availability of both of those decompositions is going to be what allows us to do Bayes' rule, and we'll get to that in a second. Okay, so we'll use this form of it, right? And we'll say that on the left-hand side we have probability of A given C, and on the right-hand side we have A given C times probability of B given AC. Well, the only way that can happen is if the probability of that equals 1, probability of B given AC equals 1, or in other words, B is certain, right? It's got probability of 1, which we understood to mean certainty. So in the end, what we've gotten is from major premise, conditional on the minor premise, the conclusion is certain. In other words, we've just restated the Aristotelian syllogism. We've got back to strong deduction as a special case of this product rule of probabilities. Okay? So far so good. Now what about our weak syllogisms? Okay, so let me put this over here. I need more room. Product rule in its other form. Okay, our weak syllogism, if you remember, was something like, let's say C, the major premise again, is that A implies B, but our assumption is that B is true, right? And our question was, what does this do to the plausibility of A? Right, so we have sort of evidence that a condition is true, we have a logical implication, but we want to know how does that update or inform our plausibility estimates. And what we can say, again, by the same kind of reasoning as we did before, is that, so let's write probability of A given B and C, okay, that's here. We're going to take that as probability of A and B given C divided by probability of B given C, which we can just as well write as the other form. Okay, so just write that here. Probability of A given C times probability of B given A and C divided by probability of B given C. Okay, so all we've done there is substitute for the joint probability of A and B the second form of the product rule, basically the reverse direction of breaking it down according to first A and then B given A. And now it's pretty clear how the plausibility works, right? So we have some assumption about a condition. Maybe it's like our condition that the guy was a thief and he was robbing the jewelry store. If you remember, a police officer observing a guy sneaking around. He has maybe some background assumption about how likely it is that somebody's a thief. But then he updates that assumption based on updates that plausibility based on the observation that the guy is sneaking around and is wearing a mask and doing other shady things. So the question is, all right, well, what is our updated plausibility of the hypothesis that he's a thief? Well, it's whatever we started with without having observed that information, now times a factor, which is the ratio of how likely that behavior would be under the assumption that he's a thief to just how likely it is ordinarily, right? So you can see right away that if, let's say, this condition B is made more plausible, right, by assumption A. In fact, in this formulation, since B is derivable from A, we actually know that it's equal to 1, right? It's certain. Then this condition is going to get updated in its plausibility, right? So probability of B given C, whatever it is some small number, maybe less than 1, and we're just taking 1 over it and multiplying by our base probabilities. Okay, so in particular, if this is very unlikely behavior, like this is something that you never would really expect to see, and then you do see it, the amount that increases the plausibility of this hypothesis that the guy is a thief is a great amount, right? So this ratio is going to be some very large number, and our probability, our plausibility is going to go way up. Okay, so that is going to be, as I said, our main rule for doing statistical inference, and our main, in fact, our only real tool that we need to apply probability to some real problems. Okay, so if we just kind of recap where we've gotten to, what we have now is actually some very powerful tools that are going to allow us to do a lot of problems in practice. So these two rules, as you remember, are derivable from kind of elementary ideas of what consistent logical reasoning should consist of. So we just sort of systematized that, we wrote it down, we worked out the mathematical consequences of it, we did kind of a change of scale to make them on the most convenient basis possible. We called that the probability. We then have these ordinary, what we recognize as the sum and the product rule, as Jaynes calls it, of probabilities, which, if we then think about any other kind of logical statement, are going to be enough to give us the probabilities of any kind of compound statement we want, right? So remember, last time we talked about building up complex statements as conjunctions of, or combinations of ands and nots. So we now have the and the not, so we can build up lots of complex statements that way. If we write that equation two ways, right, this is our main kind of theoretical insight of probability, we can break down a joint probability in two ways by thinking about each proposition first, so either B first and then A conditional on B, or A first and then B conditional on A. And the fact that we can do that two ways and we have to get the same number according to our desideratum of consistency means that we have an equation, okay, that we can re-express as a way of updating our probability assignment of a hypothesis based on some observed data. Okay, so again, just kind of a sneak preview of everything that's to come the rest of the book. This argument is going to be the template for how we do statistical inference. So the term here, this probability of A given C, is going to be what's called our prior. So this is the probability that we assign to a hypothesis based on just background information about the way the world works and kind of what things we think are true. B given A, that probability is going to be what's called our sampling distribution, and this is the one that ordinary orthodox statisticians are obsessed with. It's the one that tells you how frequently you get data conditional on some hypothesis of what's generating those data, right? So that is going to be an important ingredient. What's also then going to be important is how else might you get that data not conditional on the hypothesis. So this is what's called the likelihood ratio, and basically what we have to think about in computing this term in the denominator is all the other ways that we could get the data from other hypotheses, other explanations, and what their associated probabilities are, and then we build up the total probability unconditional on the hypothesis of just how likely we expect that data to be. Okay, so this is a term that orthodox statistics kind of doesn't recognize, but since we do, we're going to end up with a rule and a way of updating our probability assignments for the hypothesis we're interested in based on the ratio of these two things. And in particular, if our hypothesis, like the police officer's hypothesis that the guy's a thief, explains our observable data so much better than other hypotheses might, we're going to update this ratio by some large number, and it's going to make our hypothesis nearly certain, right? So in this case, the guy sneaking around based on the idea that he's a thief is near certain. Based on just general background information is very unlikely, so that ratio elevates our probability assignment that we think somebody's a thief to near certainty. And so this just basically encodes quantitatively the kind of weak syllogistic reasoning that we understand that we do every day, and it puts it in a very kind of rigorous framework. Okay, so the rest of the chapter, there's some more discussion about some particular examples involving the principle of indifference and drawing balls out of an urn. We'll get to that next time. I think that it fits more naturally in the next chapter, which is about hypothesis testing and sampling theory. And that's really all going to be about this numerator term B. So we'll talk about that next time. But again and again, we're going to be using basically this one rule, well, these two rules, but this one in particular, the product rule, to move information from one side of a conditional statement to the other side. So this is going to be the really powerful rule, and actually in the end, the only theorem that we need to have in probability.